In this lesson, we continue our look at electromagnetic induction by considering Lenz's law. Here are the objectives. The previous lesson was about Faraday's law. We've seen that a changing flux through a loop of wire generates an EMF, which in turn can drive a current. And Faraday's law, stated as an equation, is this, that the EMF is equal to the negative of the time rate of change of the magnetic flux through a loop of wire. We've also seen that the flux through a loop of wire is equal to BA cos theta, where B is equal to the magnetic field strength, A is equal to the area of the loop of wire that is within the magnetic field, and theta is the angle between the normal to the plane of the loop of wire and the magnetic field. Any of these things can be changing, and it's that change that gives us a change in flux. Faraday's law and this equation allowed us to connect that change in flux to the EMF that's generated, and we could do so quantitatively. We did, however, ignore this negative sign, and I mentioned that that negative sign has to do with the direction of the EMF and therefore the direction of the current. We're going to look at that direction now. Let's go back to some examples that we looked at with bar magnets in an earlier lesson. We said that if this is the north pole of a bar magnet, then it's going to have a magnetic field emanating like this out of it. Remember that the magnetic field's direction is the direction the north pole of a compass would point, and so the arrows are pointing up in this direction. And if this is a loop of wire, if the bar magnet is stationary relative to the loop of wire, then we get no current because there's no changing flux. This flux is staying constant. But if I were to move this bar magnet upwards, now I have an increasing flux because I have denser field lines here, the magnetic field is stronger, and so I have an increasing flux through this loop of wire. If I think of my equation, BA cos theta for my flux, theta and A are not changing, but B is increasing as I bring a stronger magnetic field into the loop. So I have an increasing flux, and we saw, or at least we stated previously, that the current that is going to be induced in the wire is going to go in that direction. It's going to be going clockwise here. In order to understand that or predict that, we need to remember our right-hand rules for the magnetic field of a coil of wire or a solenoid. Remember that a current traveling through a wire generates its own magnetic field, and that when that wire is bent into a loop or into a solenoid, then we can use a particular right-hand rule to figure out the direction of that magnetic field. And as a reminder, that right-hand rule is this. You take your fingers and coil them in the direction that the conventional current is traveling around the loop or the solenoid. So in this case, I'm pointing my fingers to the left and then I'm coiling them into the page. So they're going to look something like this. So there are my fingers coiling into the page. Here's my wrist. And that leaves my thumb pointing downwards. My thumb is going to be left pointing in the direction of the north pole of this loop or solenoid. So again, coil your fingers around here into the page. So my fingers are coiling like that, clockwise, like this current is. And then that's the direction of the north pole. So the north pole, I'll write it in green here to match the current. The north pole of this loop is below the loop, and the south pole is going to be above the loop. Notice that the north pole is opposing the north pole that is coming towards it. Again, remember the current is only induced in the loop when the bar magnet is moving. So if you were pushing this bar magnet upwards, you would feel a resisting force as you're bringing like poles together. And that's always going to happen. The current is going to be induced in such a way that it opposes the change you are trying to impose upon it. Let's continue with another example to make this clearer. Again, I have a north pole of a bar magnet near a loop of wire, but now I'm going to move the bar magnet downwards. In this case, the current is going to be going in the opposite direction. Here it's going to go counterclockwise. And again, using the right-hand rule, now I would be pointing my fingers to the right of the page and coiling them this way, and that would leave my thumb pointing upwards. That means that the north pole of this loop of wire is up here and the south pole is below. And again, we see that it's opposing what we're trying to do. As we pull the magnet downwards, we're actually generating a south pole here at the loop of wire, which is going to attract the north pole and again try and resist what we're doing. This south pole again is being generated by the current in this loop of wire because currents generate magnetic fields. Let's do one more example, and this time we'll use this principle to tell us which direction the current is going to be going. So now I have a south pole closest to the loop of wire, and so I need to turn my arrows around because remember they're pointing in the direction that the north pole of a compass would point, and I'm going to move this bar magnet upwards. Now, using the same principle as before, we said that the magnetic field generated by the loop of wire is going to oppose the change that we are trying to force upon it. And so if we're pushing a south pole towards the loop, it's going to try and resist us by putting a south pole there that's going to push back. So this end would be the north pole. Now if we work our right hand rule backwards, we point our thumb towards the north pole, our fingers are going to be coiling in this direction, telling us the direction of the conventional current. So the current must be going in this direction in order to put a north pole up here and a south pole down here, and we know that this must be a south pole because it's going to resist the change we're trying to impose upon it. So all of this is captured in Lenz's law, which states that the direction of any induced EMF and current is such as to oppose the change that caused it. The direction of any induced EMF and current is such as to oppose the change that caused it, like we were seeing above. Now make sure that you are looking at the change in flux, not the flux itself. That's a common point of confusion. We're interested in how the flux is changing, not its overall direction. Let's look at a few more examples to make sure that this is clear. So now we're going to look at fields that are going into the page. That's why we've got X's in all of these, and we've got a loop of wire that is laying perpendicular to that field. We're asked to draw the direction of current flow in each case. So in the first case, the field is getting stronger. You could imagine that as more X's like this. So if the field is getting stronger into the page, then the magnetic field from the loop of wire must point out of the page to oppose that change. Using the right hand rule and pointing our thumb in the direction of the magnetic field of the loop of wire, our thumb would therefore have to point out of the page. Again, the external field is getting stronger into the page. We want to oppose that, so we need a magnetic field pointing out of the page. We point our thumb out of the page towards ourselves, and that leaves our fingers coiling in this direction, that is counterclockwise around the loop. That means that the current that's leading to that magnetic field must be pointing counterclockwise around the loop. In the next example, we again have an external field that's pointing into the page, but now the field is getting weaker. You can imagine it getting less into the page, if you like. In order to oppose that change, as Lenz's law states, we actually need to reinforce the field into the page because it's getting weaker. To do that, using the right hand rule, we point our thumb into the page, and pointing our right hand thumb into the page leaves our fingers coiling in this direction now, clockwise, meaning that the induced current in the loop must be going clockwise in order to oppose the change, the weakening, that is inducing the current in the first place. So comparing these first two examples, notice that it's not the overall direction of the field that we care about. In both cases, the overall direction of the field is into the page. It's the direction of the change that matters. In this one, the field is getting more into the page, so our induced current needs to generate a field out of the page. And in this one, the field is getting more out of the page, or less into the page, and so our induced current needs to generate a field going into the page. The induced current has to oppose the change, not the overall field. Let's look at one more example. Here we've got a loop in a field that's going into the page and the loop's getting smaller. If the loop's getting smaller, so it's moving in like this, then we are getting a decreased flux through the loop. And because the flux here is pointing into the page, that means we're getting a decreased flux into the page. Again, the current needs to now create a magnetic field that increases the flux into the page to keep things from changing. And so just like in this second example, we would have a current that's going clockwise. Again, by the right-hand rule, to reinforce the flux into the page, point your thumb into the page, and that leaves your fingers coiling in that direction. So Lenz's law allows us to predict the direction of a current when it's induced by a changing magnetic flux through a loop. Lenz's law turns out to be just another statement of the law of conservation of energy. Now, that might not be immediately obvious, but let's take a look at an example. This is the same example we've used before. We've got the north pole of a bar magnet moving towards a loop of wire, and we've said that Lenz's law tells us that the current must be going in that direction because that makes this a north pole and this a south pole, and then these like poles will resist each other. So as you try and move the bar magnet towards the loop, it actually resists you, and you would feel a force resisting you as these like poles repel each other. Now let's imagine for a moment that that were not true. Imagine that the current were in fact going in that direction, making this the north pole and this the south pole. As you were to bring the magnet closer to the loop, you generate a south pole, and these would now attract each other. As they attract each other, the flux would change more quickly because the bar magnet would now be pulled in faster. A more rapidly changing flux would increase the current around this loop. An increase in current would generate a greater magnetic field, and then the process would repeat. You get this positive feedback loop that was generating energy from nowhere. And that can't happen, and as a result, it's not a south pole that's generated down here, it's a north pole, and the current has to go in this direction, not in that direction. So you can think of Lenz's law as a restatement of the law of conservation of energy. Also, just to note that Lenz's law is represented by the negative sign in Faraday's law. If this is Faraday's law, I'm going to write the version with n loops here. This negative actually tells us the direction of the EMF, and the direction of the EMF tells us the direction of the current. So you could actually use this negative to figure out the direction of the current, but in general I find it easier just to use the kind of approach with the right-hand rule that we've used here. So this has been a look at Lenz's law, which allows us to predict the direction of an EMF and current induced when the magnetic flux through a loop is changing.